This is Lecture 3G for Calculus 1 on the product chain and quotient rules. I'm using here the derivation of the product rule as given by Thomas in his calculus book. I scanned this picture from his book. It's nice, and I'm using the same notation that he did there in the margin. Okay, so the idea is the product rule applies to taking the derivative of two functions that have been multiplied together. I'm going to call the two functions u and v. Could have called them f and g, but he used u and v in this picture, so we'll continue with that notation. When I multiply the two functions together, I'm creating this area right here. Now, both of them are functions of x. When I'm taking the derivative, you remember setting up that difference quotient, we had x and then we took another point some distance away at x plus h. So when that happens, u of x, some distance away, will become u of x plus h. I'm assuming here that u and v increase whenever x does. Okay, so if I change x to x plus h, u changes to u of x plus h. Similarly, v of x would change to v of x plus h. I would like to know the pink and blue area, the area of that pink and blue sections, right? Because that would represent the change. In derivatives, we're looking at the change, right? So how do I compute those pink and blue sections? One way would be to take the area of the whole outside of the rectangle. That would be u at x plus h times v at x plus h. That would give me the whole rectangle, and then subtract off the white area that I colored pink or colored yellow on the inside, and the result would just be that pink and blue border, the area of the pink and blue border. There's another way to write this, and I'm showing it right here. I could try to take just the area of the little pink and blue sections themselves. Okay, I'll get rid of some of this other stuff. If I take u at delta x and multiply by the change in v, here's the delta v here, then I would get the area of the pink section. If I took v at delta x and multiplied by the change in u, and here's the little change in u here, I would get the blue section. The only trouble is the little square in the corner got counted twice, so I have to subtract that off. I'm going to take this second representation for the area of the pink and blue sections, and I'm going to divide it by h. So here's the result of dividing by the h. I have the second expression for the pink and blue areas. That would be u at x plus h times delta v, and v at x plus h times delta u, subtracting off the little corner, which is delta u times delta v. Remember, in math, the Greek capital delta means change. It usually means a substantial change, and we want the infinitesimal change, and taking the limit as that infinitesimal change goes to 0, and that's what we're going to work towards here. Anyway, here we're dividing by h. Okay, I'm going to break this out into 3 fractions. The first fraction have u at x plus h times delta v over h. The second fraction is v at x plus h times delta u over h. And then the third one, you subtract off delta u delta v divided by h. Now we take the limit as h goes to 0. Of course, I wrote h goes to 0 plus because I'm restricting h to be positive. That's not a problem. Okay, if h goes to 0, u at x plus h just becomes u of x. V at x plus h just becomes v of x, and the delta u or the delta v both go to 0. That's fine when the delta u and the delta v are by themselves, but when they're divided by h and both things are going to h together, you have to take the limit. So what is the limit of a change in v over h? That's just its derivative, dv by dx. Right. Again, what is the change? What is the limit as h goes to 0 of the change in u over h? That's the derivative again, du by dx. All right. For the little corner piece, delta u is going to 0. When I'm taking the limit here, I can write it this way, delta u, and then take the limit only over dv by dx, and I would end up with 0. You could have done it the other way and set delta v to 0, and then when you take the limit, you would have delta v times du by dx, and that again would be 0. So the last term dropped out. I only have those first two, and here is the product rule. I say that the derivative of two functions multiplied together, u times v, is u, hold u constant, take the derivative of v. Then hold v constant and take the derivative of u. I will say this for f and g. If I have two functions multiplied together, f times g, the derivative of f times g is f times the derivative of g plus g times the derivative of f. So here are two examples. So in this first case, I have a function x squared, and I have it multiplied by the sine of x. So f is x squared, g is sine x. I want to take the derivative. First, I hold the f constant, so I just hold the x squared constant and take the derivative of g. Then I hold the g constant and take the derivative of f. Okay, so the derivative of sine x is cosine x. That's how I get the first term, x squared cosine x. For the second term, the derivative of x squared is 2x. So there's my result. X squared times the cosine of x plus 2x times the sine of x. Again, I hold the x squared constant, take the derivative of sine. Then I hold sine constant, take the derivative of x squared. Here is what the product rule is not. The product rule of f times g is not equal to the derivative of f times the derivative of g. If you added them together, it would be, if you said the derivative of f plus x, that is the derivative of f plus the derivative of x. But when it comes to the product, it's different. So I'll show you what this is not. I'm taking the derivative again of those two functions. Okay, x squared times sine of x. I cannot just take the derivative of x squared and multiply it by the derivative of sine squared. You see what the answer would be? 2x cosine x. It is not the same. The answer is x squared cosine x plus 2x times the sine of x. Here's another example. I'm going to take the derivative of the function f, 12x plus 6, and I'm multiplying it by e to the x. So I hold the 12x plus 6 constant and take the derivative of e to the x. Then I hold the e to the x constant and take the derivative of 12x plus 6, and there's my result. 12x plus 6 times e to the x, because the derivative of e to the x is e to the x. For the next term, I have 12, because the derivative of 12x plus 6 is just 12, times e to the x, which was held constant. All right, again, I'm going to show you what the product rule is not. So I just wrote it again for emphasis. So here I am, say I'm taking the derivative of 12x plus 6 times e to the x. I cannot just take the derivative of the f function and multiply it by the derivative of the g function. That would give me 12x. In that case, it happens to be the last term, but it's not the right answer. To find situations in which the chain rule has to be used, you need to recognize situations in which there were two functions, f and g, composed together. If they just wrote f composed with g, that would make it easy, but it's usually not the case. The functions have already been composed together, and you are shown the result. So you have to sort them back out into their f and g. In a sense, sort them into their outside function and their inside function. So we'll just go through some examples here. Here is 12x plus 9, all raised to the 32nd power. I'm going to say the outside function is something raised to the 32nd power. I could have put an x here, but I just want to put a blank for emphasis. So it's something raised to the 32nd power is the outside function. The inside function is 12x plus 9. Here we have x raised to the minus 1. The outside function is something raised to the minus 1. The inside function is a sine of x. Now I've got sine of 4x plus 6. The outside function is sine. The inside function is 4x plus 6. In this case, 2 is raised to the power 24t. The outside function is 2 raised to something, and the inside function is 24t. You see all these little functions, the f and g's here, you know how to differentiate already. Here's e to the tangent of x. So the outside function is e raised to some power, e to the x, and you know the derivative of that is e to the x. Now you have the inside function as tangent of x, and the derivative of tangent is secant squared. Okay. One more example. I have the square root of 45z squared plus z cubed. The outside function is the square root. The inside function is 45z squared plus z cubed. Sometimes you have situations when it's more than 2 functions composed together. There might be 3. Here's an example. I'm going to have the sine of 3x plus 4 raised to the 4th power. The most outside function would be x to the 4th. Then the first inside function would be the sine, and that would be an outside function for 3x plus 4. So here you would have f composed with g composed with h. The outside function would be x to the 4th, composed with the sine of x, composed with 3x plus 4. Here's another example. E raised to the tangent of x squared. So the outside function is e to the x, or e raised to something. Then the first inside function is tangent of x, and the most inside function is x squared. Before I show you the proof for the chain rule, I'm just going to make the statement of the chain rule and then give 2 examples so you can see how to use it. There's 2 ways to think of the chain rule. You can think that you have some y and it's composed with g. Then when I go to take the derivative of y with respect to x, I'm taking the derivative of the functions already composed together. I have to sort out which one is which, but I take the derivative of the outside function, just as though it were a function of x, and evaluate it at the inside function. That gives you the composition. Multiply it by the derivative of g. The second way to think about it is to think that y is equal to some function of u, and u happens to be g of x. Then when I take the derivative, I take the derivative of f with respect to u. Then I take the derivative of u with respect to x. All right, some comment is in order here. If you look at this, you might say, oh, the du's cancel, and you get df by dx. And that is not the case. Remember, d by du is an operator, means take the derivative with respect to u. d by dx is an operator, it means take the derivative with respect to x. Okay, so here I'm going to give you the example, the same example, and I'll use the chain rule both ways so you can see it. Some ways it's kind of semantics, in some ways there's some subtle differences. Okay, but here's the chain rule. You get the same answer both ways. I'm taking the derivative of sine of x raised to the 5th power. The outside function is x to the 5th. The inside function is the sine of x. So when I'm using the chain rule in that first formulation of it, I would take the derivative of f with respect to x, evaluate it at g of x, then multiply it by dg by dx. So I need to find all the little pieces parts for this thing. All right, first I need df by dx. Well, I said f was x to the 5th, so I'm taking, well, that should be a 5 there. So I'm taking the derivative with respect to x of x to the 5th, and I get 5x to the 4th. Now I need to evaluate that result at sine x. So wherever there's an x, I put sine of x, and here I have that term. Now I need to take the derivative of g of x to get this term, and that ends up being cosine of x. Okay, multiplying all that together, I have 5 sine x raised to the 4th, which is my, okay, I'll change color here. Okay, so I have 5 sine x to the 4th, which is just this term right here. And then for the dg by dx, I have this term. Okay, now I'm going to do the same problem again. Sine x raised to the fifth. But I'll do it using that other notation. Get the same answer. Okay, so I'm going to say y is some function of u, and u is g of x. So if y is, so that means that u is the sine of x, and f of u is u to the fifth. So instead of using the x's, I'm using u's. Right. This way I write this chain rule is dy by dx equals df by du times du by dx. Right. So I have to get those pieces. The derivative of f with respect to u is the derivative of u with respect to x to the fifth, and you know what that is, 5u to the fourth. But I know what u is, so I'll just substitute it. Okay, then du by dx is just taking the derivative with respect to x of sine x, and I get the cosine of x. So now I just put these together. All right, get some of this yellow off of here. So the first term I get is 5 sine x to the fourth. I got that from here, and it was this term. And then I need the next term, which is du by dx. Computed that over here, and that's where I got. You don't necessarily, when you go to take these derivatives, after a while you will not have to separate it out where you do, for example, this whole thing and then this whole thing and put it together. You kind of just eyeball it and do it right in one step. But there's nothing wrong with breaking things out either. Now we can use the chain rule to extend that power rule. Before, the power rule was restricted to exponents that were integers. No, natural numbers. I think it was just natural numbers, what we did before. Okay, so the idea is if you have something raised to the fourth power, could you have something raised to the arbitrary nth power, where n could be negative, positive, irrational, whatever. Okay, and when I applied the chain rule, all I had to do was take the derivative, here's the derivative of the outside function, then multiply it by the derivative of the inside function. For polynomials, it's the same thing. All right, if I have anything raised to the nth power, I can put the n here, take the derivative of the polynomial, raise it to the n minus 1, and then take the derivative of the polynomial. So now this is a general case of that rule. I have the derivative with respect to x of anything raised to the nth power. So first I take the derivative of the outside function, which is, say, x to the n, and that will give me the n u to the n minus 1. Then I take the derivative of whatever was being raised to the power. So now we've extended the power chain rule to have more general terms under the exponent. Most books list a quotient rule, and I think it's easier to use the chain rule, or a combination of the product and chain rules. So if I have f divided by g here, I could just as easily write f times g inverse. Or, no, I'm sorry, g to the minus 1. Okay, what am I saying? Okay, how would I take it if... So at this point, I'll use the product rule. That means I hold, in this case I held a g constant, the second term constant, took the derivative of the first, then hold the first constant and take the derivative of the second. To take the derivative of this g to the minus 1, I have to use the power law, or the chain rule in the power law. Okay, so here we go. I'm taking the derivative of f over g, which I'm going to write as f times g inverse. To apply the product rule, I hold one of these terms constant. I'll hold the second one constant. Take the derivative of the first. Then I hold the first constant and take the derivative of the second. All right. This term, which I'll put all in yellow, is no problem. And now, to take the derivative of this g to the minus 1, I have to use that chain and power law. G to the minus 1, green, I guess. The minus 1 comes out in front. The g turns into a minus 2. And now I have to take the derivative of g with respect to x. So here's the power law written with negative exponents instead of with fractions. You could put this all over a common denominator of g squared, and you would get the power law or the quotient law that's written in the book. I usually don't bother with that quotient law. Just no reason to memorize a new rule. All you need is the product rule, and then once you take the derivatives as though they were products, then you have to apply the chain and power law to get the derivative of the denominator. So here's a proof of the chain rule. I'm going to recall that the derivative was a limit of slopes, delta y over delta x, of those secant lines as delta x went to 0. And then we call that f prime. I'm going to define a new term that I'll call epsilon, which is just a term. Right now it has nothing to do with a limit. Let's just let it be epsilon. And it is the difference between the slope of the secant line and the actual derivative. It is a difference between the slope of the secant line and the slope of the tangent line. So this is sort of like a measure of the error of the difference between your secant line and the actual derivative. So I could rearrange this and isolate the delta y, and I could write it like this. Delta y equals the derivative times delta x plus epsilon times delta x. I'm working with the chain rule, so I have f composed with g, and I'm going to use the formulation that y equals f of some function u, and u equals g of x. So here we have y being the result of composing f and g. I'm going to break each part out as their own little derivative, just like I did before. So delta u over delta x would be the derivative of the secant line. G prime is the actual derivative. Epsilon 1 is going to be sort of the measure of the error. So I can write delta u equals g prime delta x plus epsilon 1 times delta x, and I could write both of those, combine both of those and put delta x on, factor it out. I can do the same thing here for the change in y. Delta y equals this derivative times delta u minus how far off you are. Epsilon 2, again, is going to be measure a little bit of that error. Now I'm going to substitute delta u into my expression for delta y, and I get this. Okay, the change in y equals the derivative of f plus its little error times the derivative of g plus its little error times delta x. Now if I divide by delta x, I get dy over dx, which looks like it is the slope along the secant line, equals the actual derivative of f plus the error times the actual derivative of g plus the error. If I take the limit, epsilon 2 and epsilon 1 go away because those were the difference between the secant lines and the tangent line, and there you get it. F prime times g prime, or dy du times du dx, and that's the chain rule. What we did in that other slide was just do things in general. Now we really have to take the derivative at some point, so we kind of have to go over this again. So let's say that g at a equals some value, has a value b. Right? And because they're composed, f is going to take that b and map it into something. So we're looking at g evaluated at a, giving us b, and f evaluated at b. So now we have a specific point. This change in u equals g prime at a times delta x plus that first little error times delta x. We repeat this down here, and we have this delta y equals f prime at b times delta u plus that little bit of error times delta u. Now I substitute delta u in the first line into the delta u in the second line, and I get this expression. Delta y equals the derivative of f at b plus that error, epsilon 2, times the derivative of g at a times the error times delta x. Divide by delta x. This looks like your secant line. Take the limit, And when you take the limit, again, the epsilon 2 will go to 0 and the epsilon 1 will go to 0 because now your secant line has turned into your tangent line, and you get f prime at b times g prime at a, which is the same as taking the derivative of f with respect to x and evaluating a g of a, because g of a is b, times the derivative of g with respect to x. So here's a summary of the rules. I'm going to write the chain rule in the second method. F and g are composed together. Y equals f composed with g. So I'm going to write y equals f, and that f is some function of u, and that u is some function g of x. Then when I want to take the derivative of y with respect to x, then I take the derivative of f with respect to u, multiply it by du by dx. For the product rule, f and g are multiplied together. To take the derivative, hold f constant, take the derivative of g. Then hold g constant and take the derivative of f. And the last line is just the quotient rule written as though f over g equals f times g to the minus 1. So first you use the product rule to get the two terms, and then when you are taking the derivative with respect to x of g to the minus 1, you have to use the chain rule.